The Sukhoi Su-57, NATO reporting name Felon, is a stealth single-seat twin-engine multirole fifth-generation jet fighter being developed in 2002 for air superiority and attack operations. The aircraft is a fifth-generation fighter program of the Russian Air Force. Sukhoi's internal name for the aircraft is T-50. The Su-57 is the first aircraft in Russian military service to use stealth technology. Its maiden flight took place on January 29, 2010 and it entered service on December 25, 2020. The fighter is the world's fourth operational fifth-generation stealth fighter aircraft after the F-22, F-35, and J-20. According to Sukhoi Company, the fighter is designed to have supercruise, supermaneuverability, stealth, and advanced avionics to overcome the previous generation fighter aircraft as well as ground and naval defenses. The Su-57 is intended to succeed the MiG-29 and Su-27 in the Russian Air Force. The prototypes and initial production batch are to be delivered with a highly upgraded Lilka AL-31 variant, the AL-41F1, as an interim power plant, while an advanced clean sheet design engine, currently designated the Aviatsii A30, is in final stages of development, expected to be available after mid-2020s. The aircraft is expected to have a service life of up to 35 years. In 1979, the Soviet Union outlined a need for a next-generation aircraft intended to enter service in the 1990s. The project was designated the I-90 and required the fighter to have substantial ground attack capabilities and would eventually replace the MiG-29s and Su-27s in frontline tactical aviation service. The subsequent program designed to meet these requirements, the MFI, resulted in Mikoyan's selection to develop the MiG-1.44. Though not a participant in the MFI, Sukhoi started its own program in 1983 to develop technologies for a next-generation fighter aircraft, resulting in the S-37, later designated Su-47. Due to a lack of funds after the collapse of the Soviet Union, the MiG-1.44 program was repeatedly delayed and the first flight of the prototype did not occur until 2000, 9 years behind schedule. The MiG-1.44 was subsequently cancelled and a new program for a next-generation fighter, PAK FA, was initiated. The program requirements reflected the capabilities of Western fighter aircraft, such as the Eurofighter Typhoon and F-22 Raptor. In 2002, Sukhoi was selected over Mikoyan as the winner of the PAK FA competition and would lead the design of the new aircraft. To reduce the PAK FA's developmental risk and spread out associated costs, as well as to bridge the gap between it and older previous generation fighters, some of its technology and features, such as propulsion and avionics, were implemented in the Sukhoi Su-35S fighter, an advanced variant of the Su-27. Final assembly is to take place at Komsomolsk-on-Amur. NPO Saturn is the lead contractor for the interim engines. Saturn and MMPP Salyut will compete for the definitive second-stage engines. In 2004, the fighter's conceptual design was completed and approved by Russia's Defense Ministry, with Alexander Davydenko selected as the chief designer. Funding of the program began in 2005. Flight testing began with T-51, the first prototype aircraft, on January 29, 2010. Piloted by hero of the Russian Federation Sergei Bogdan, the aircraft's 47-minute maiden flight took place at Knopos-Jangi Airport in the Russian Far East. The second prototype, T-52, was originally planned to fly in late 2010, but this was pushed back to March 2011. The first two prototypes lacked radar and weapon control systems. On March 14, 2011, the fighter achieved supersonic flight at a test range near Komsomolsk-on-Amur. The T-50 was displayed publicly for the first time at the 2011 MAX Airshow. The aircraft has a blended wing-body fuselage and incorporates all moving horizontal and vertical stabilizers. The vertical stabilizers tow inwards to serve as the aircraft's air brake. The aircraft incorporates thrust vectoring and has adjustable leading-edge vortex controllers designed to control vortices generated by the leading-edge route extensions, and can provide trim and improve high angle of attack behavior, including a quick stall recovery if the thrust vectoring system fails. The advanced flight control system and thrust vectoring nozzles make the aircraft departure resistant and highly maneuverable in both pitch and yaw, enabling the aircraft to perform very high angles of attack maneuvers such as the Pugachev's Cobra and the Bell maneuver, along with doing flat rotations with little altitude loss. The Su-57 has a climb rate ranging from 1,100 feet per second to 1,180 feet per second. The aircraft makes extensive use of composites, with the material comprising 25% of the structural weight and almost 70% of the outer surface. Weapons are housed in two tandem main weapons bays between the engine nacelles and smaller bulged, triangular section bays near the wing root. Internal weapons carriage eliminates drag from external stores and enables higher performance compared to external carriage, as well as enhancing stealth. The Su-57's aerodynamics and engines enable it to achieve Mach 2 and fly supersonic without afterburners, or supercruise, a significant kinematic advantage over previous generations of aircraft. Combined with a high fuel load, the fighter has a supersonic range of over 930 miles, more than twice that of the Su-27. Extendable refueling probe is available to further increase its range. In the Su-57's design, Sukhoi addressed what it considered to be the F-22's limitations, such as its inability to use thrust vectoring to induce roll and yaw moments and a lack of space for weapons bays between the engines, and complications for stall recovery if thrust vectoring fails. Pre-production T-50 and initial production batches of the Su-57 will use interim engines, a pair of NPO Saturn Izdaliye 117, or AL-41F1, augmented turbofans. The engine is a highly improved and uprated variant of the AL-31 that powers the Su-27 family of aircraft and produces 21,000 lbf of dry thrust, 33,067 lbf of thrust in afterburner, and has a dry weight of approximately 3,530 pounds. The engines have full authority digital engine control and are integrated into the flight control system to facilitate maneuverability and handling. The AL-41F1 is closely related to the Saturn Izdaliye 117S engine, or AL-41F1S, used by the Su-35S, with the latter's separate engine control system being the key difference. The AL-41F1 engines incorporate thrust vectoring nozzles whose rotational axes are each canted at an angle, similar to the nozzle arrangement of the Su-35S. This configuration allows the aircraft to produce thrust vectoring moments about all three rotational axes, pitch, yaw and roll. Thrust vectoring nozzles themselves operate in only one plane. The canting allows the aircraft to produce both roll and yaw by vectoring each engine nozzle differently. The engine inlet incorporates variable intake ramps for increased supersonic efficiency and retractable mesh screens to prevent foreign object debris being ingested that would cause engine damage. The AL-41F1 is to also incorporate infrared and RCS reduction measures. In 2014, the Indian Air Force openly expressed concerns over the reliability and performance of the AL-41F1. During the 2011 Moscow Air Show, a Su-57 suffered a compressor stall that forced the aircraft to abort takeoff. Production fighters from mid-2020s onward will be equipped with a more powerful engine known as the Izdaliye 30. Compared to the AL-41F1, the new power plant will have increased thrust, lower costs, better fuel efficiency, and fewer moving parts. The engine also has glass fiber plastic IGVs to reduce the aircraft's radar signature. Those features, along with subsequently improved reliability and lower maintenance costs, will improve the aircraft performance and reliability. The Izdaliye 30 is designed to be 30% lower specific weight than its AL-41F1 predecessor. The new engine is estimated to produce approximately 24,054 lbf of dry thrust and 39,556 lbf in afterburner. Full-scale development began in 2011 and the engine's compressor began bench testing in December 2014. The first test engines were completed in 2016. The new power plant is designed to be a drop-in replacement for the AL-41F1 with minimal changes to the airframe. On December 5, 2017, the second Su-57 prototype, fitted with the Izdaliye 30 engine, first took off from the Gromov Flight Research Institute. The 17-minute test flight was carried out by Sergei Bogdan, Sukhoi chief test pilot. The Izdaliye 30 engine was installed on the port side engine position while the AL-41F1 remained on the starboard side. The Izdaliye 30 features a new nozzle with serrated flaps compared to conventional ones on the AL-41F1 nozzle. On February 8, 2018, Russian Deputy Minister of Defense Yuri Borisov said that the new engine's performance was difficult to judge, because all we have had is this one flight. Everything seems normal, but many flights are to be performed. As a rule, such trials take 2 to 3 years. By December 6, 2019, Rostec has conducted 16 flights of the Izdali A-30 engine to check its characteristics in various flight modes, specifically, the operation of the vectoring jet nozzle and the oil system at negative overloads. Everything seems normal, but many flights are to be performed. As a rule, such trials take 2 to 3 years. By December 6, 2019, Rostec has conducted 16 flights of the Izdali A-30 engine to check its characteristics in various flight modes, specifically, the operation of the vectoring jet nozzle and the oil system at negative overloads. The Su-57 prototype has 2 tandem main internal weapon bays, each approximately 15.1 feet long and 3.3 feet wide, and 2 small triangular section weapon bays that protrude under the fuselage near the wing root. Internal carriage of weapons preserves the aircraft's stealth and significantly reduces aerodynamic drag, thus preserving kinematic performance compared to performance with external stores. The Su-57's high cruising speed is expected to substantially increase weapon effectiveness compared to its predecessors. Vimpel is developing 2 ejection launchers for the main bays. The UVK 50 liters for missiles weighing up to 660 pounds and the UVK 50U for ordnance weighing up to 1,500 pounds. For air-to-air combat, the Su-57 is expected to carry 4 beyond visual range missiles in its 2 main weapons bays and 2 short-range missiles in the wing root weapons bays. The primary medium-range missile is the active radar homing K-77M, an upgraded R-77 variant with ESA seeker and conventional rear fins. The short-range missile is the infrared homing, heat-seeking, K-74M2. An upgraded R-74 variant with reduced cross-section for internal carriage. A clean sheet designed short-range missile designated KMD is being developed to eventually replace the K-74M2. For longer-ranged applications, 4 large Izdali A-810 beyond visual range missiles can be carried, with 2 in each main weapons bay. Reportedly, the fighter will also be able to carry the long-range hypersonic R-37M missile. The main bays can also accommodate air-to-ground missiles such as the KH-38M, as well as multiple 550 pounds Cobb 250 or 1,100 pounds Cobb 500 precision-guided bombs. The aircraft is also expected to carry further developed and modified variants of KH-35UA anti-ship missile and KH-58 USHG anti-radiation missile. For missions that do not require stealth, the Su-57 can carry stores on its 6 external hardpoints. BrahMos Aerospace Chief A. Shivathanupillai stated that there was a possibility of the installation of BrahMos supersonic cruise missile on the Su-57 FGFA derivative. New hypersonic missile with characteristics similar to the KH-47M2 Kanzal ALBM is also being developed for the Su-57. The missile is to have intra-body accommodation and smaller dimensions to allow it to be carried inside the Su-57's main central weapon bays. A new missile appeared to be a derivative of R-77, was displayed during Vimpel's 70th anniversary on November 18, 2019. The new missile's length was approximately just 2/3 of R-77's 12 feet length, and thought to be designed to fit inside the triangular wing root bays under the Su-57's wings. The aircraft has an internally mounted 30mm autocannon near the right Levcon root. The cannon is the lightest in 30mm class with 50 kg weight, and could fire up to 1,800 rounds per minute. The cannon can fire blast fragmentation, incendiary and armor-piercing tracer rounds and is effective against even lightly armored ground, sea and aerial target up to 800 meters for aerial target and 1,800 meters for ground target. The cannon is equipped with autonomous water cooling system, where water inside the barrel jacket is vaporized during operation. The Su-57 has a glass cockpit with 2 15-inch main multifunctional LCD displays similar to the arrangement of the Su-35S. Positioned around the cockpit are 3 smaller control panel displays. The cockpit has a wide-angle head-up display. Primary controls are the joystick and a pair of throttles. The aircraft uses a 2-piece canopy, with the aft section sliding forward and locking into place. The canopy is treated with special coatings to increase the aircraft's stealth. The Su-57 employs the NPP's Zvezda K36D5 ejection seat and the Sukhoi 50 life support system, which comprises the anti-G and oxygen generating system. The 66 pounds oxygen generating system will provide the pilot with unlimited oxygen supply. The life support system will enable pilots to perform 9-gram maneuvers for up to 30 seconds at a time. and the new VKK-17 partial pressure suit will allow safe ejection at altitudes of up to 75,000 feet in November 2018. The system is said to be at the final stage of tests, the stage of state flight tests, and the test pilots are already flying in this equipment. The pilot gear also consisted of a digital helmet which connected to onboard photo and video cameras to improve pilots' situational awareness. It also features pupils' movement detection system to allow automatic targeting unlike previous Soviet fighters. There is also a survival kit consisting of a pan, antenna, signal mirror, 16 cubes of sugar, first aid kit, 2 match boxes, a signal pistol with charges, 1.5-liter bottle of water, machete knife, radio beacon, and portable radio. The pilot could use the survival kit's container as a boat or waterproof sleeping bag if necessary. The main avionics systems are the SH-121 multifunctional integrated radio electronic system and the 101KS Atoll electro-optical system. The SH-121 consists of the NO36 Bielka radar system and L-402 Himalayas electronic countermeasures system. Developed by Tihomирov NIAP Institute, the NO36 consists of the main nose-mounted NO36101 X-band active electronically scanned array radar, or active phased array radar in Russian nomenclature. With 1,552 TR modules and 2 side-looking NO36B101 X-band ESA radars with 358 TR modules embedded in the cheeks of the forward fuselage for increased angular coverage. Moreover, the side-looking radar could enable the Su-57 to employ extreme beaming tactic while still able to guide its own missile. The suite also has 2 NO36L101 L-band transceivers on the wing's leading-edge extensions that are not only used to handle the NO36SH Pokosnik friend or foe identification system but also for electronic warfare purposes. Computer processing of the X and L-band signals by the NO36 use computer and processor enable the system's information to be significantly enhanced. In 2012, ground tests of the NO36 radar began on the third Su-57 prototype aircraft. The L-402 Himalayas electronic countermeasures suite made by the Kaluga Research Radio Engineering Institute uses both its own arrays and that of the NO36 radar system. One of its arrays is mounted in the dorsal sting between the 2 engines. The system was mounted on the aircraft in 2014. Radio-telephone communication and encrypted data exchange among various aircraft and also command centers will be provided by the S111 system, developed by Polio. The system will be based on a modular concept and could be installed not only on the Su-57, but also on various aircraft, helicopter, and drones. Its effective range of operation is up to 930 miles, a spokesman said. The system's reliability is guaranteed by the multiple redundancy of the main functions and cutting-edge technical solutions, as well as a wide range of radio channels. Built on the basis of laser gyros and quartz accelerometers, it autonomously processes navigation and flight information, determines position and motion parameters in the absence of satellite navigation, and can integrate with GLONASS. It is guaranteed to last at least 10,000 hours, and can be used universally, not only in airborne, but also in marine and terrestrial equipment. In 2016, CRET announced it is developing a multifunctional video processing system called Okotnik to increase the Su-57's target detection range as well as to improve automatic detection and tracking of targets. In April 2017, UAC announced that a new next-generation integrated avionics suite has started flight testing. According to Dmitry Gribov, a chief designer of the new Kompleks, the new avionics suite, called Integrated Modular Avionics Combat Systems, will replace a system designed in 2004 called Baguette used on the Su-35. The still-in-development system has more than 4 million lines of code. The IMA-BK makes use of indigenous Russian multi-core microprocessors and a new indigenous real-time operating system called Bagger OS 4000. The new avionics suite also makes use of fiber optic channels with a throughput of more than 8 gigabits per second, which is up from 100 megabits per second for traditional copper wires. The new IMA-BK integrated avionics suite is designed to automatically detect, identify, and track the most dangerous targets and offer the pilot the best solution to engage an enemy. The new system will take control of almost all of the key sensors of the aircraft, radar, navigation and communication that in previous aircraft were controlled by separate computers, then simultaneously performs the role of an electronic pilot, electronic navigator and electronic flight engineer. A monitoring system mimicking a living organism's nervous system will allow real-time assessment of the aircraft's condition and predict the remaining life of the composite parts of the aircraft by combining optical fibers, with sensitivity to mechanical influences, with the aircraft's network system. The information about the aircraft's condition will be transmitted via laser beam through the optical fiber woven into the structure. It will decrease the aircraft's maintenance costs and allow parts to be repaired preemptively, thus improving flight safety. Prototype Su-57 aerodynamic condensation at Max 2015. The Su-57 is intended to be a fifth-generation multirole fighter aircraft and the first operational stealth aircraft for the Russian Air Force. Although most information is classified, sources within the Sukhoi company and Defense Ministry have openly stated that the aircraft is to be stealthy, super-maneuverable, have supercruise capability, incorporate substantial amounts of composite materials, and possess advanced avionics such as active phased array radar and sensor fusion. The aircraft has a blended wing-body fuselage and incorporates all moving horizontal and vertical stabilizers. The vertical stabilizers tow inwards to serve as the aircraft's air brake. The aircraft incorporates thrust vectoring and has adjustable leading-edge vortex controllers designed to control vortices generated by the leading-edge root extensions, and can provide trim and improve high angle of attack behavior, including a quick stall recovery if the thrust vectoring system fails. The advanced flight control system and thrust vectoring nozzles make the aircraft departure resistant and highly maneuverable in both pitch and yaw, enabling the aircraft to perform very high angles of attack maneuvers such as the Pugachev's Cobra and the Bell maneuver, along with doing flat rotations with little altitude loss. The Su-57 has a climb rate ranging from 1,100 feet per second to 1,180 feet per second. The aircraft makes extensive use of composites, with the material comprising 25% of the structural weight and almost 70% of the outer surface. Weapons are housed in two tandem main weapons bays between the engine nacelles and smaller bulged, triangular section bays near the wing root. Internal weapons carriage eliminates drag from external stores and enables higher performance compared to external carriage, as well as enhancing stealth. The Su-57's aerodynamics and engines enable it to achieve Mach 2 and fly supersonic without afterburners, or supercruise, a significant kinematic advantage over previous generations of aircraft. Combined with a high fuel load, the fighter has a supersonic range of over 930 miles, more than twice that of the Su-27. Extendable refueling probe is available to further increase its range. In the Su-57's design, Sukhoi addressed what it considered to be the F-22's limitations, such as its inability to use thrust vectoring to induce roll and yaw moments and a lack of space for weapons bays between the engines, and complications for stall recovery if thrust vectoring fails. On 27 April, 2020, it was reported by the Izvestia that the Su-57 hydraulic systems were planned to be replaced with electromechanical drives, improving the aircraft's combat survivability, stealth characteristics, maneuverability and reducing the maintenance complexity. According to the report, the first flight of a modernized Su-57 was scheduled for the middle of 2022, with the trials of the electric fighter version to take at least 2 years. The Su-57 is planned to be the first operational aircraft in Russian Air Force service to use stealth technology. Similar to other stealth fighters such as the F-22, the airframe incorporates planform edge alignment to reduce its radar cross-section, RCS. The leading and trailing edges of the wings and control surfaces and the serrated edges of skin panels are carefully angled to reduce the number of directions the radar waves can be reflected. Weapons are carried internally in weapons bays within the airframe and antennas are recessed from the surface of the skin to preserve the aircraft's stealthy shape. The infrared search and track sensor housing is turned backwards when not in use and its rear is treated with radar absorbent material to reduce its radar return. To mask the significant RCS contribution of the engine face, the walls of the inlet ducts are coated with RAM and the partial serpentine ducts obscure most of the engine's fan and inlet guide vanes. The remaining exposed engine face is masked by a radar blocker similar in principle to that used on the F-18. According to Sukhoi's radar blocker patent, the slanted blocker grid is placed in front of the IGV at a distance of 0.7, 1.2 times the diameter of the duct. The fuselage of the aircraft is coated with RAM to absorb radar emissions and reduce the reflection back to the source. Due to the extensive use of polymeric carbon plastics composites, the aircraft has 4 times fewer parts compared to the Su-27, weighs less and is easier to mass produce. The aircraft canopy is made of composite material and 70 to 90 nanometers thick metal oxide layers with enhanced radar wave absorbing to minimize the radar return of the cockpit by 30% and protect the pilot from the impact of ultraviolet and thermal radiation. Izvestia reported that from 2021, Su-57 will be supplemented by a dozen of protective covers, separately for the wheels, the lower, central and rear fuselage, wings, cockpit, nozzle, stabilizers, air intakes and other parts of the structure, to protect the plane from bad weather and hide them from reconnaissance means. The Su-57's design emphasizes frontal stealth, with RCS reducing features most apparent in the forward hemisphere, the shaping of the aft fuselage, the seams between parts, and rivets are much less optimized for radar stealth compared to the F-22. However, during MAX 2019, some observers noted that the craftsmanship of the fuselage was finer than expected from Russian aircraft and looked smooth despite the rivets. The second serial production Su-57 also seemed to have a significantly better tolerance on its skin panel than the previous prototype. The combined effect of airframe shape and ram of the production aircraft is estimated to have reduced the aircraft's RCS to a value 30 times smaller than that of the Su-27. Sukhoi's patent for the T-50 prototype stealth features cites an intention to reduce average RCS to approximately 0.1 to 1 square meter, compared to the Su-27's RCS of approximately 10 to 15 square meters. Like other stealth fighters, the Su-57's low observability measures are chiefly effective against high-frequency, between 3 and 30 GHz, radars, usually found on other aircraft. The effects of Rayleigh scattering and resonance mean that low-frequency radars, employed by weather radars and early warning radars, are more likely to detect the Su-57 due to its size. Such radars are also large, susceptible to clutter and are less precise. On May 16, 2020, it was reported by RIA that one of the Su-57 prototypes had been tested in an unmanned mode, with the pilot acting as an observer of the plane's actions. According to the latest Russian military doctrine, which considers the Russian armed forces as defensive forces meant to protect the country and its allies while maintaining a strategic deterrence capability, this fighter follows a different design philosophy when compared to Western fifth-generation fighter. With its forward-optimized stealth and infrared sensor, the aircraft could be considered as a counter-stealth fighter meant to get as close as possible to adversary stealth jets before engaging them, diminishing the enemy's stealth advantage and forcing them to a close-quarter dogfight, where it has the theoretical advantage due to its 3D thrust vectoring and supermaneuverability. According to Bill Sweetman, the Su-57's high operational speed and altitude combined with its standoff weaponry could be hinting at its role as a sort of airborne sniper, designed to fly fast and high to engage enemy support aircraft. This claim is supported by Russia's intentions to adapt the new R-37M air-to-air missile with range of more than 300 km to the Su-57's armament, giving it a role similar to the MiG-31BM interceptors. Newly designed anti-ship and hypersonic weapons like Kh-47M2 Kinzhal could also enable the Su-57 to perform as a maritime strike aircraft. The Su-57 could also serve as a testbed for advanced AI and man-on-man teaming technologies intended for use in a future sixth-generation fighter program.